Good morning, everyone. Today, I am excited to present the SAFES architecture, developed at the National Center for High-Performance Computing in Taiwan. We will explore how we orchestrate granular access control for highly sensitive omics data within our trusted cloud platform. Established in 1991, NCHC is Taiwan's sole national facility for shared high-performance computing. We deliver world-class supercomputing, cloud services, and AI platforms, acting as an enabler and enhancer to drive cross-disciplinary scientific discovery and innovation. Our mission rests on 4 pillars. We deploy national-scale AI computation, advance key high-performance computing projects, establish secure big data ecosystems for sensitive domains, and manage Taiwan's core research broadband and network infrastructure. To support these missions, we pursue 3 strategic goals: national-level data services, digital governance, and cross-domain applications. This is built on a secure cloud infrastructure incorporating zero-trust networks, proxy encryption, and stateless computing. The Trusted Cloud Platform, or TCP, provides a highly secure cloud environment with advanced storage encryption. It offers flexible compute instances through VMs and Kubernetes, complemented by intelligent execution assistance to simplify complex workflows. The TCP architecture logically segregates workloads. Users authenticate via our Identity and Access Management System. The architecture is split into a sensitive zone for restricted assets and a general zone for public utilities, managed through strict, controlled data exchange paths. This partitioned model ensures that raw sensitive data never leaks into the public area. However, as omics datasets grow, meeting the absolute highest standards of strict regulatory compliance poses an ongoing challenge for standard cloud environments. A prime example of our work is our partnership with Taiwan Biobank. We host massive genetic datasets, securing over 1.3 petabytes of data with 3-2-1 backup strategies, and support a rigorous multi-step data release pipeline. Similarly, the Taiwan Cancer Moonshot Project relies on NCHC to manage multi-omics datasets. Our Data Stay-in-Place protocol enabled landmark oncology discoveries published in Cell and Cancer Cell while fully protecting patient privacy. To manage these massive files efficiently in HPC, we use granular file ACLs and hard links. This zero-copy approach prevents redundant storage. Still, we must address the risk of data leakage at the virtual user endpoints. To solve this endpoint challenge, we developed SAFES, the Sensitive Data Access and File Exchange System. We cleanly decoupled the platform into SAFES Core for authorization logic and SAFES Gate for physical exchange mechanics. When integrated into TCP, SAFES Core connects to the sensitive zone as read-only to map access policies. Meanwhile, SAFES Gate handles secure read-write import and export pipelines, isolating raw storage from direct exposure. We rely on iRODs for this. Under the Data Virtualization tier, files appear to users as virtual collections. We can register and assemble these logical directories without moving or copying a single physical file on NCHC storage. For secure collaboration, moving petabyte-scale data is highly impractical. Instead, we manage access rights directly within the ICAT directory. The system mimics Unix permissions, enforced strictly under defined administrative policies. In SAFES Core, we register physical paths to virtual directories. Users in different project groups are dynamically authorized to mount only their approved virtual directories, achieving precise, highly granular access controls. The workflow is simple. The system administrator imports files into the VM, and the daemon logs their cryptographic hashes in Postgres. After identity verification via LDAP and iRODs, authorized users access this data as read-only. For import and export, SAFES Gate acts as a secure airlock. Files going out require a user request and strict hash verification. A data administrator must manually review the payload before authorizing the download. To guarantee reliability, Safes is deployed in a high-availability cluster across 3 physical Proxmox servers. Load balancing through HA proxy, clustered PostgreSQL databases, and redundant iRods instances ensure 0 single points of failure. In conclusion, the TCP and Safes integration successfully realizes the 5 Safes framework. By securing the data, projects, people, settings, and outputs, we offer a highly trustworthy and legally compliant research environment. Our work ensures that vital scientific and clinical breakthroughs can happen swiftly without compromising patient confidentiality. We look forward to collaborating with global partners to advance secure high-performance computing.